Right. Good morning, everyone. Good morning, maybe. Gives me great pleasure to be here this morning to give you this presentation talking about potential field data, much like this beautiful data set from the Browse Basin, which has just been released today. I doubt it's the case in this building, nor in that building down the road in Deakin, but I think potential field data sometimes could be considered a little bit as the neglected sibling of the geophysical family. So in a moment of gratuitous self-promotion, I did announce this presentation on Facebook, and some of the responses I had were pretty interesting and probably reflect some of this potential field indifference. So just drill a hole, Ron, do some seismic, give me 100 million and I'll be able to get the data for you. I think that's pretty typical. Yeah, you've got to drill a hole in the end, I suppose. Well, nothing a forked stick wouldn't do more cheaply. Ranging then to complete indifference to, well, this is from someone in the building here, potential field as well. But reassuringly, there was some positive comments in there, and this is what I hope to do today, to talk to you a little bit about the potential of potential field methods. So what am I going to talk about? Well, first you might be asking, what's potential field data? Of course, that's gravity and magnetic data. So I want to talk to you a little bit about what that is. I'll touch on also what a petroleum system is, just some of the key elements of that, because I think it sets the context, although I think that'll be pretty familiar to most of you. I'm going to give some case studies, some examples here of using potential field data on Australia's continental margin. Now, of course, in a presentation like this, much of this work I can't claim credit for myself, but the people who've contributed or done the work or led the work will be, of course, be acknowledged as we go through. I'm going to talk a little bit about crustal architecture of the margin, sediment thickness, basement composition, and then end on this little point here on the challenge of ambiguity of uncertainty. We're always faced with this issue when we're dealing with gravity and magnetic data. So in that context, what more can we do? Can we get better constraints on the crust? And can we somehow include process in our modelling? Rather than just doing static modelling, can we think about the processes that are involved in our modelling? So starting with potential field data, we'll start with the magnetic field of the Earth. Well, okay, I'll do both of them here first. On the left, magnetic measurements. If we make measurements of the magnetic field, we're not going to just get the magnetic signal of the rocks that we're interested in. So we're interested in this stuff down the bottom here, the variations in magnetisation of crustal rocks, maybe upper mantle rocks as well. But when we measure the magnetic field, we're going to get all these other things as well. So we're going to get the magnetic field that mainly arises from the fluid motion in the liquid outer core. And then there's going to be all the effects of the solar wind interacting with the ionosphere and the atmosphere. And those sort of things have always got to be accounted for. When we're dealing with gravity data, it's pretty much the same situation. What we measure is far more than what we actually want. We want to know something about the mass or the density distribution within the Earth, but when we measure the Earth's gravity field, we're mainly going to see the effect of its shape and its rotation. And also little things like the gravitational pull of the Sun and the Moon can also be significant. So what it comes down to is if we make these measurements, they have to be corrected for all these non-geological effects. We've got to try and get rid of them before we can say something about geology. So let's have a look at the Earth's magnetic field. If we measured it, this is pretty much what it would look like. Okay, so what we see there is not much geology, but most of what we see here is the main field that arises from the core. It's more than 95% of what we measure. Then there's these secular variations because of the fluid flow in the outer core, the flow currents that are changing with time. So it might vary by around 5% over a period of around 100 years. There's also those diurnal variations in the ionosphere that can induce quite large changes over the course of a day if we're making an aeromagnetic survey, so we have to correct for them. And then ultimately end as these features related to the crustal magnetism. So if we do something, we correct for all these other things, then we end up with some kind of magnetic field which then starts to look a little bit more like geology. And as that one spins around there, you'll be able to see, maybe make out, well, here comes Australia now, might be familiar to a lot of us, some of the features in the seafloor. So we've got to get rid of all those things to see what we're really interested in. And as I mentioned, it's pretty similar for the gravity field. If we measured the Earth's gravity, this is pretty much what we'd see. We'd see it would be very high gravity at the poles, lower gravity in the middle. You can see the numbers here. If you remember back to the high school physics or whatever, acceleration of gravity was always around about 9.8. And you can see it varies a bit. But what we're after here is a very, very small percentage of this total thing that we measure. So what we measure is, again, the effects of the Earth's shape and its mass. So the Earth is kind of a squashed sphere. So the gravity is higher at the poles than at the equator because we're slightly closer to the centre of the Earth. There's the Earth rotation effects. You've got a centrifugal force as the Earth spins, and that centrifugal force is greater at the equator than at the poles. There's these tidal variations. They're pretty insignificant in the whole scheme of things, but they can be significant, of course, when we're trying to relate things to geology. There's elevation variations as we go up and down over topography. We're getting further or closer to the centre of the Earth. And then there's also the topographic mass, or the mass of the topography in the oceans, which we have to take account of as well. Ultimately, we get to these deep Earth variations, lateral variations in density, which we might be interested in some cases, but not always. And if we correct for all these other things, we finally get to the geology-related, or the crustal density variations we might be interested in. So this next one spinning around, we've taken account of the Earth rotation, and again you can see it's still higher at the poles, slightly lower at the equator. You can start to see some features jumping out in the gravity here. If we make some more corrections for the shape of the Earth, we can use mathematical formula to approximate the gravity effect of this rotating sphere, or squashed sphere, sorry. And then we can start to see here, this is what we would be familiar with as the free air gravity anomaly, and you can see it's starting to reflect much better what we would expect from the geology. Although in the marine areas especially, and also in the onshore areas, it still maintains a very strong correlation with topography. So that's another thing we want to have to correct for. If we do that, we end up with the Bouguer gravity anomaly. And when we look at this one, it's showing quite well the continents stand out as relatively low values of gravity because they're thick, relatively low density bodies. And the oceanic crust, where the high density mantle is quite shallow, is dominating in the ocean areas. So that's also telling us something geological, but maybe again not quite what we want. We can do some kind of regional residual field separation, so it's basically removing the longer wavelength effects related to the deep lateral variations, and then we'll end up with something that's reflecting what we would hope to see more in the geology. So that's the process we've got to go through to get to something that's useful in our gravity measurements. And I did mean to throw in a quick acknowledgement to Neil Caldwell here for his efforts over the last week at quite short notice to get these fancy things spinning around here. What's a petroleum system? Okay, this may be familiar to many of you in the room as well, but let's touch on that quickly too. We'll start with a very schematic, idealised sort of sedimentary basin here. It's made up of some crystalline basement. It might be older metamorphic rocks. It's been intruded by some magmatic rocks. We've got this basin here. It's got a fault in it, an offset in the basement, maybe a little bit of inversion on those layers in there. And the sedimentary basin comprises these permeable sandstones and maybe some layers of organic rich impermeable sediments as well. So when we think of a petroleum system, we're going to think of the source, the reservoir and the seal. So we have to have somewhere where we get the hydrocarbons from. And in this little simple diagram here, they're being squeezed out of these rocks down here, or cooked out of the organic rich rocks quite deep in the basin. So this would be our source region. And the critical thing with the source region is that we've got to have enough temperature to cook everything up and have it be squeezed out of those source rock layers at depth. So we want some kind of heat. So the heat things, it depends on what's in the basement. For example, maybe these intrusions help, or simply whether the basement is deep enough and thick enough that the temperatures can be sufficient. So obviously when we generate some hydrocarbons, they'll migrate into a reservoir. I've also thrown in a little CO2 reservoir up here because we also deal with them a little bit these days. And then we've got to have some kind of seal to keep those things in the reservoir. So in a simple schematic sense, this is what a petroleum system would be. Now, when it comes to the work that GA does, we don't necessarily work in all of this space. Our main thing would maybe be related to this sort of source area. Is there enough sediments to generate hydrocarbons? How deep is the basin? And those kind of things. And if we think of these petroleum systems in a basin analysis framework, and this is a slide stolen from an earlier DGAL from a few years ago from Heike Struckmeyer, and we think about where does this all fit together in a basin analysis sort of framework. And when we're looking at basins, obviously what we want to do is first collect all of our data, and there's the potential field data, the gravity mag data sitting in there in amongst the seismic and well data and all the other sorts of data. We'd use those data then to say something about the nature of basement, so what's its composition, how is that going to affect the generation of hydrocarbons, the basin forming mechanisms, the basin architecture, accommodation history, depositional environments, and all those things would feed into building structural models, looking at the sequence stratigraphy, so the sequence of the sediments in the basin, timing of events, and then we come down to this thing here, the petroleum systems. Here at GA, in some cases we would go as far as doing a petroleum system model, but not always. So the link to make here is this path from potential field data and the other data through to the petroleum systems. And so the examples I want to show now are maybe going to focus more on these aspects here. So using potential field data to say something about the components or the input that goes into this petroleum system modelling. What's the role for gravity and magnetic data? How does it work, or how can we use it? And to try and illustrate that, let's look at this little basin again here, and I've now coloured up in the top here for what we might expect for the density of those rocks in the basin and also the magnetic susceptibility. The magnetic susceptibility is just really how magnetised those rocks are. So you can see for the density one, the seawater up on top would be very low density compared to the rest of it. Quite a low density in the sediments, a moderate sort of density in the basement. And some of these intrusions, well, depending on their composition and makeup, they might be high density or low density, or maybe even about the same as the basement. It's a similar picture for the magnetic data, for the magnetisation of these rocks. The water and the water would have zero susceptibility essentially, and the sediments would have very low magnetic susceptibility. And again, what's in the basement would vary depending on the composition of the rocks and things down there. In this case, the fault itself may be in some cases magnetised, depending on what sort of minerals have been deposited in the fault. So when we think of these sort of contrasts and properties between the different rocks, that tells us what we can do about how we can use the potential field data in the basin studies. So we can use them to estimate the depth to basement, because there's a big contrast between the sediments and the basement in both cases. So that means it'll generally have quite a strong gravity or magnetic signature. So the sediment thicknessing really comes down to the question, are the sediments thick enough to help us generate hydrocarbons, assuming we've got some kind of suitable source down at depth? But the potential field data is not necessarily going to help you answer that question. We can use it to characterise the basement. So these contrasting physical properties in the basement are also going to tell us, or you're going to have a signal in the potential field data which tells us something about their distribution, their composition and similar things. And so the influence of the basement is important because it influences how much extension we might have in the basin, which then relates to how much accommodation space, so how much space we've got to fill with sediments, and also then the thermal history of the basin. So whether, was there peaks in heat flow during the evolution of the basin? I'm not going to touch on this one so much today, but we can also use the properties of these things to map out faults and volcanics. We might have offsets in the basement which will have a magnetic or gravity signature, or like I said, the fault itself may also have some kind of signal. And that then has an important influence on the reservoir, whether the reservoir has been cut by faults, for example, allowing some of these hydrocarbons to escape. Okay, so now I'll come on to some of these case studies. I'll start off here with a map of the Australian region, roughly coloured up for how much maybe we know about these basins. So you can see these dark blue ones here, particularly on the northwest shelf, the Bonaparte, the Browse and the Carnarvon, northern Carnarvon Basin. We've got quite a lot of seismic and well data, so these basins are all pretty well constrained. There's a lot of other basins, variable colouring here. It's a little bit subjective in the way I've divided it up here, but these may be considered more the frontier basins. So depending which basin we're in, the balance of the weight of how important potential field data is might depend on how much other data we've got in these basins. And I'm going to give you a few examples here. I'm going to start out in the Capel and Fouse basins, out on the Lord Howe Rise here, talking about this fundamental question of what's the sediment thickness. I'm going to switch over to the Wallaby Plateau and talk a little bit about crustal architecture. So the Wallaby Plateau is a region that's reasonably well unknown. We don't know so much about it. Is it a piece of extended continental crust? Is it something else? I'll move down to the Perth Basin and I'll give you an example of how we can maybe infer something about the composition of basement. And that's where I'll start to get into this point about ambiguity and uncertainty in the modelling you might do with potential field data as well. And the last example, we'll come to the Browse Basin, some of the early work I've been doing there, looking at incorporating process in the modelling of the basins up here. Okay. Some of these case studies here I'm going to talk about, they'll be necessarily quite brief. I'm not going to talk about everything, but we have put together a paper which is just coming out in Marine and Petroleum Geology, which does summarise a lot of these case histories, and if you want to get more detail I can certainly arrange for you to get a copy of that. Right, the first question. Capel and Fouse basins, looking a little bit at sediment thickness. So the Capel and Fouse basins are a long way out from the east coast of Australia. Let's have a little bit of a look here. There's a map here. You can see the coastline here. The Lord Howe Rise is this submerged continental ribbon which separated from Australia when the Tasman Sea opened up. So the Capel and Fouse basins, we would consider them as very much frontier basins. They're a long way away, they're in quite deep water, we don't know much about them. But part of the work that Geoscience Australia did in the mid-2000s was a lot of new data was acquired, so seismic reflection data, swath bathymetry, marine gravity and magnetic data. So we had an opportunity to try and answer some of these key questions. And one of the main questions would have been, is there enough sediment in this basin to facilitate the generation of hydrocarbons? So I'm going to zoom into this area now. The next slide will show basically the depth of the sediments, the thickness of the sediments here, based on the interpretation of the seismic reflection data, which was acquired on this network of lines that are shown here. So we have this interpretation of basement. It's published in a record headed up by Jim Colwell when he was here several years ago now. So we can come up with an interpretation of the from the seismic data of how deep the basin is, but how reliable is that interpretation? There are still uncertainties involved in interpreting the seismic data. There's, I guess, different people might interpret different things in different ways. Sometimes the data doesn't resolve things very well. So how reliable is the interpretation, and can the uncertainty somehow be quantified to give us some kind of handle on the uncertainty in that? The results I'm going to show here are from a method that was referred to by Peter Petkovich as he was doing this as modelling while interpreting. And this is basically a process of repeatedly testing the seismic interpretation with 3D gravity modelling. So as the seismic interpreters came up with a new interpretation, Peter would take this, build a 3D model, compute the gravity response, compare it to the observations, and then give them feedback. Well, it doesn't really work here, it does work here, and that's an iterative way of giving people information about how we can improve the interpretation. So what's shown in the picture on the right here, at the top here is the observed Bouguer gravity for these Capel and Faust basins. And then the other image is various different generations of this series of modelling. And overall he did 84 different series of forward gravity models for this basin. And you can see that there's a variable agreement in the fit between the observed data and the calculated. This one, an early one for example, perhaps you can see it doesn't fit so well. So then the interpretation gets revised, some of the properties are revised. And we ultimately end up with a computed gravity anomaly like this, which is reasonably similar to what's up here, and that is the one that's based on that final seismic interpretation. We can take it an extra step if we go and do some inversion modelling, testing a whole range of models to get some kind of handle on the uncertainty in the pick to the depth of the basement. So essentially this process allows us to run millions of different models with slightly varying physical properties each time. And what's shown in this image here on the left again is this basement depth from the seismic interpretation. On the right is what we get from the gravity model after this inversion. Now this is the best fitting basement from that modelling, and you can see the calculated gravity here from that, and it's a better fit than even in the previous example. But we can go one step better because we've got all these different models. We can say, okay, well, if we accept some kind of degree of tolerance for misfit between the observed and the calculated gravity, we can say something about, well, what sort of tolerance or error do we have on the depth to the basement. And the next image will show a seismic section. I should just quickly show you, this is the seismic section coming through here of this part of the basin. And so you can see here the seafloor would be here, you can see the sedimentary layers below. And what's plotted here, the red line, is the seismic basement, so that's the basement as interpreted from the seismic reflection data. The blue line is the best fitting basement derived from the inversion modelling, and you can also hopefully see these green lines either side of the blue line, which give us an indication of the 90% confidence interval for that depth to basement. So that's basically saying that between those green lines we can derive a basement which is an acceptable fit to the gravity data. And what you can see in this, when you compare the gravity basement to the seismic basement, in some areas they agree reasonably well, but in other areas there can be quite big differences. So again, this is telling us either we've got to revise the seismic interpretation, or there are some factors we haven't considered in the gravity modelling, which might be, for example, variable density in the basement, which in this case wasn't included. So by following this sort of modelling while interpreting approach, we can come up with some kind of estimates of the uncertainty on the thickness of the sediments that we're trying to infer. Okay, moving on to the next example, coming out to the Wallaby Plateau, where we want to look a little bit at crustal architecture. The Wallaby Plateau, there's a figure here from a paper by Alexei Goncharov and Gabe Nelson, who's sitting here somewhere as well, yes. A map of the Wallaby Plateau here. The Wallaby Plateau sits out here off the West Australian coast. Here's Shark Bay in here. And it's a bathymetric high. You can see it's relatively shallow compared to some of the surrounding areas. And it's quite deep water. We don't know much about it. And it was recently added to Australia's maritime jurisdiction through all those law of the sea boundary sort of processes. So the key questions here might be, well, very fundamental, is this a piece of continental crust? Because if it's a big build-up of just volcanic rocks, for example, it's probably not particularly interesting from a hydrocarbon resources perspective. Is there any thick sediments here? And the question then is, well, can gravity and magnetic inversion help the modelling here? And the work that I'm going to let's just go here to have a quick look at one of these seismic lines here. We're looking at this little piece of the line in here. And one of the features of this Wallaby Plateau from the seismic interpretation was these divergent dipping reflector sequences. And they appear quite similar to seaward dipping reflector sequences, which are a characteristic of very volcanic-rich continental margins. They're a characteristic of the processes that are involved in forming the margin. And the question is, well, are these DDRs really like SDRs, the seaward dipping reflector sequences, in the sense of, are they volcanic or are they sedimentary? And if they're sedimentary, that's obviously much more useful to us than if they're all volcanic. So Alexei and Gabe were involved in doing a bit of an analysis of the seismic velocities, and my interpretation of their results is also suggesting, well, it's a little bit ambiguous. You can't really say either way whether it's really volcanic or really sedimentary. And the question is, okay, can we get any further also with the gravity data, or the gravity and magnetic data doing the inversion? And that's where James Goodwin came along in his graduate rotation a few years back. And he built and ran a whole lot of gravity and magnetic inversions on the NCI supercomputer over at ANU there. Very large areas, quite high resolution, so lots of cells in these inversion models, just to give us some kind of idea of what the crust is like in this part of the world. And the models that he came up with, they give the density and the magnetic susceptibility, so these physical properties that we can relate to geology and tell us something about what's going on in the crust. And just to summarise the results, I'll show you some pictures in a moment. The densities that we get in this inversion are typical of continental crust down to depths of about 25 kilometres. So it does seem to suggest that, well, this could well be a nice piece of continental crust. Those divergent dipping reflector sequences, they tend to be associated with areas of high magnetic susceptibility, which means they're going to have probably going to have some kind of volcanic component in them. So I'll show you now a couple of depth slices through these models that James built. And here's the first depth slice here at a depth of 20 kilometres. On the left here is density, and on the right is the magnetic susceptibility. You can see here this is the seismic reflection lines that are shown there. What's also plotted on here is the dip direction and the extent of those divergent dipping reflector sequences. And when you look at the Wallaby Plateau, the outline of it shown there, the densities here, these little blue patches, they're quite crustal type sort of densities. We're quite deep down probably in the lower crust here. So it's looking like this is a block of continental crust with typical sort of densities. And you maybe can argue there's some little cores of continental crust here, and if you look and look at these little way these arrows are pointing, they tend to point away from these little low density cores to this plateau. If we're looking at the magnetic susceptibility here, again you see a similar thing. There's maybe these patches where we don't have very high magnetisation. And again, these DDRs maybe seem to be associated with regions of relatively high magnetic susceptibility. If we look slightly shallower in the crust, it's a similar sort of story. So a big patch of relatively low density, and again, these areas of relatively high magnetic susceptibility. So that's given us some kind of basic knowledge about what the crustal makeup is in this continental or this plateau offshore. So moving on to the Perth Basin, we want to have maybe a bit of a look here at the basement composition. A quick map here of the Perth Basin. The Perth Basin is reasonably well known in the onshore parts of the basin. The coastline comes down here, you can see. So in this part of the world here, this Dandaragan Trough. Up further north, there are some smaller hydrocarbon discoveries in the onshore areas here. But these offshore basins, the Hootman Subbasin, the Zeewick Subbasin, even the Abrolhos Subbasin, are reasonably well unknown. So maybe want to ask some fundamental questions. What is the nature of these outboard frontier subbasins? And are they similar to the highly prospective sheared margins that are starting to be realised or discovered on, for example, in the central Atlantic on the African coast, where they've recently found in a similar tectonic setting some quite large hydrocarbon deposits? So the first thing to look at here is characterising the basement. And I mentioned earlier, I think that the basement influences petroleum systems, the amount of stretching that could go on depending on the rheology of the basement. so how much space there can be for the sediments to fill in. And also the composition influences the thermal history, which is again then important for that generation of hydrocarbons. So the process that's going on here is we're basically starting with the magnetic data. We're using the magnetic data to map where the source bodies are, so we're saying something about where those magnetic sources are in the data set. And this is based on a method that Michael Morse adopted in the Bass Strait, looking at this so-called tilt angle filter. That'll mean something to some people, but others it's not so important. So we can do this, we can isolate where these source bodies might be, we can then map the basement type from outcrop and wells. That's how we get our hard knowledge of what the basement is actually made up of. We can then try and associate this information on the basement type with the source polygons for where the magnetic sources are in the magnetic data, and then we can extrapolate to areas where we don't have any of these hard constraints from the wells and the outcrop. So I'll just go through that sequence, and this is based on work that the composition part that Lisa Hall did a year or so ago. So we start with the magnetic data. Maybe just point out again the coastline coming down here. The highest sort of magnetic intensity here is the Yilgarn block, so the Darling fault coming down here, and some of the basins out here. So we start with the magnetic data. We can compute this tilt angle filter, and basically that normalizes things and it has things either as positive or negative. And it's these red areas that theoretically are supposed to relate to something down below, which is related to something that's magnetic, that is giving rise to this magnetic anomaly. So we can then just simplify this a little bit. The grey areas here, just outlining these areas where the tilt angle filter is positive. And then what's also plotted on here is coloured up in terms of what the basement composition is. The legend will come up in a second, sorry, but basically the reds colours are granitic basement, the yellow colours are meta-sedimentary rocks, and there's one example here where it drills through into a meta-igneous basement. Now the correlations you can make here, well generally these areas with granite or granitic or meta-sedimentary basement, they don't tend to sit over the top of any of these magnetic sources. So that's maybe telling us something about the magnetic properties of those basement rocks. In contrast, there's one example here where we've got more meta-igneous basement, which we might expect to be more magnetic, having more magnetic minerals in it, sits right on top of one of these magnetic sources. So we can then, admittedly with one data point, we can extrapolate outwards and maybe make some inferences on what the basement composition is on this margin. And this is the basement map that Lisa came up with for this area. And you can see here, this is the one area where we've got this meta-igneous basement, and all those source polygons are extrapolated into an area which is probably generally characterised by these more igneous type basement, and then these other areas where it's more granitic or meta-sedimentary basement. So that's giving us some kind of means to divide the basement. We can then make some predictions about how that area is going to deform, or the different areas are going to deform based on their different properties. Okay, staying with the Perth Basin, I just want to touch on now this ambiguity or this uncertainty when it comes to modelling gravity and magnetic data. And I'm going to show you in the next slide a section through a 3D gravity model of the Perth Basin down in this area in here. So I don't want to go into the details of this model. We could argue forever about how good it is and all the things that have been done to it. But the main points to make out here, here's a section through a 3D gravity model built by a PhD student at the University of Kiel who, as part of his PhD, worked with us to do some of this modelling. And what you can see here, the yellow colours are the sediments. There's the crust in here, some kind of moho, and the mantle in below. So the dashed line here shows the initial model that Neil started with, which was just based on the direct constraints that were available for the modelling, allowing it to do its extrapolation to areas where we have no data, computing the gravity effect, and that would be this green curve here. And it's not too bad a fit, but we can maybe make some little tweaks. We can argue forever about whether those tweaks are justified or not. And that's the final model shown by the colours, which is the red curve here, which fits the data now pretty well. So we can look at a model like this, irrespective of what we say about the uncertainties and things in this model, and we can think of things like the Zeewick subbasin out here. When Neil's built the model here, it looks like a basin with quite deep sediments. They're very thick sediments, even quite far outboard from on the margin. Seem to have something that you've got to have quite steep flanks to this basin to explain this little relative gravity low down in here. And maybe this is the kind of features that are typical of a strike-slip sort of basin. Steep flanks, steep sediments. Think of something like the Dead Sea Rift. If we go further inboard, looking at the Dandaragan Trough here, this is in the onshore areas, so this would be the Darling Fault in here. And what sort of stood out here is in this model that the thickness of the crystalline crust below those sediments is quite constant. Okay? And this tells us something about probably the processes that have led to the formation of this basin here. It doesn't look like it's been stretching and thinning to produce this depression here to fill sediments into. Maybe what it looks like instead is some kind of block rotation, a rigid block rotation on the Darling Fault. So we can make some speculation about how that might look, starting out with some kind of Proterozoic basement next to the Yilgarn Craton, a Proto-Darling Fault here, and then as sort of extensions happen, this block is rotated really about the Beagle Ridge here as a rigid block rotated down, which has made the space for this basin to fill in. So these are the kind of things we can start to say about this area when we're making this sort of model. But the question, of course, is, and I've touched on that already, how good is this model? If we think of the constraints that have gone into the model, we've got 2D seismic reflection data. These data have a pretty limited extent on this part of the margin. You can sort of make out these black lines here in this image. So they're quite widely spaced, so we don't have constraints on the basement everywhere. And I'm going to show you a seismic section now here. And so the limited extent limits what we can do with the constraints, but also the basement is not always imaged in those seismic data. We don't always have the right properties to allow the signal penetration to get there and get a signal back again to say clearly this is the basement. So you can see, what you maybe can't see, there's a label here that says basement with a question mark in front of it. So we're not necessarily sure where the basement is. So that's obviously going to bring some uncertainty into the model. The other uncertainty is, well, the MOHO. And if we're going to look at a crustal model like this, we really have to incorporate the MOHO. And that's because the MOHO and the sediment, they're all intricately linked through isostasy. And isostasy is the same basic concept as what governs how much of an iceberg is below the surface of the ocean compared to what's sticking up above it. So we have to incorporate the MOHO, but the question is, okay, what do we know about the MOHO? And the next map here is just a compilation of I guess, constraints on the depth to the MOHO around the Australian margin. There's obviously a lot more information onshore, but I've obscured that just for simplicity. If we look in the area of this model profile, this is where the model is, there's almost no direct constraints on where the MOHO is. So basically, in some senses, we're having to make an educated guess at where it is. So what Niels has done in this case as well is tested a few scenarios. And what's shown here is a model, the coloured here, a model where we're assuming some kind of local isostatic balance of the lithosphere. So again, this is what you would expect in a simpler sort of sense. We make the assumption we've got thick sediments, and we'd expect that to stretch and thin the crust underneath, and we'd have some kind of shallow mantle underneath that basin. But when you look at the calculated gravity from that model, it doesn't fit in the Dandaragan Trough here at all. So the model that we settled on using is this MOHO here from an Australia-wide model that was put together by Alan Aitken, who's now at UWA. And he basically took those seismological constraints and the gravity data, did an Australian-wide plate scale inversion to come up with where this MOHO is, and this is what's gone into the model. And we can ask questions about, well, how good is that MOHO model as well? We can obviously get a much better fit to the gravity data, but there's some interesting features in this MOHO that we could ask, well, are they realistic features? So I think the point being there is that, well, we don't have so many constraints and maybe we can do better there. So when we come to dealing with this ambiguity, what can we do? And just some examples here. This is going to lead into the next example I'm going to show you. What do we do about ambiguity, all this uncertainty when we don't have enough constraints? Well, we can just ignore it, of course. We can just arbitrarily adjust everything and say, hey, look, I've got a gravity model that fits. But I think the important thing to think with these kind of models is those models are often better at telling you about what doesn't work than telling you about what does work. Because if it does fit, it's only one possibility and it's only as good as your constraints. And there may be hidden in that model plenty of places where you've adjusted that model without constraints to say something about, or to make it fit the data. But a model that doesn't fit is going to tell you, well, there's a problem area. What can I do to resolve that? Maybe I can get more data. Maybe I can think a little bit about how we can fix that. We can make some assumptions, of course, and one of them might be isostatic state. That model on the Perth Basin, first assumption might be, okay, let's assume airy local isostatic balance like an iceberg, but then we can model that and we can show, well, that doesn't work, so we've got to think of something else. Ideally, of course, we always want to have better constraints, and in the case of the MOHO in this part of the margin, yes, we'd love to have more seismic refraction surveys which are giving us seismic velocities and information on crustal structure. We can also do the approach that I talked to about before, Peter's Capel and Faust approach, where we just basically try lots of models, which ones work best, what sort of uncertainty is involved in each of these models. And that leads then to the last example I want to touch on here is this including process in the models. So taking the gravity field, rather than building a static model that just explains what the gravity field is today, can we think a little bit about the processes that led to the present day gravity field? And this can also maybe go a step towards helping us infer crustal structure and also the mechanical strength of the lithosphere. So how easy is it going to be to stretch out? So the example I'm going to show here is it's reasonably early work still from applying this process-oriented gravity modelling approach in the Browse Basin up on the northwest shelf here. How does this, what's the fundamentals of this sort of process? Well, when we're thinking about this kind of process, it's a method that Tony Watts at Oxford University has been working on for a number of years, almost his whole career, I guess. But we think about the gravity signature of a continental margin, and if we think about the free air gravity signature of a continental margin, it typically takes on a particular characteristic form. Normally we wouldn't think, okay, we don't want to worry about the free air gravity anomaly because that correlates with topography and bathymetry and all those sort of things, and we're always told use something else. But the free air gravity anomaly on a continental margin can be quite informative. And it would typically take on an effect like this. This would be a simple cross-section here showing the unextended continental crust and the extended crust out here. And you would typically have this high associated with the shelf break and then a low further outboard. So the form of this edge effect typically is like this, but it's going to change depending on what else has gone on during the formation of this margin. You know, how much rifting, how much extension, how much sediment was deposited on top of it all, how much magmatism was there underplating in underneath. That's all going to change the form of this edge effect on the free air gravity anomaly. It's also going to depend on the lithospheric strength, which is going to control the amount of extension, those kind of things. If we look at the northwest shelf here, for example, you can see quite strong changes in the edge effect along this margin. The Browse Basin's kind of outlined up here, and when you look at that, there is sort of some kind of edge here, which is probably this kind of thing here, but it's not very distinct compared to our typical example here. But if we look down on the Exmouth Plateau, you see a beautiful gravity high, which would be this one, and an outboard gravity low, which would be this one. So that signal in itself is telling you that there's some fundamental differences in what's going on in the evolution of those two parts of the margin. So this process-oriented gravity modelling approach that Tony Watts has developed is basically taking the present-day margin configuration. This is what we see here. Here's our extended crust. It's got some sediments on top of it. Here's our free air anomaly edge effect. What happens is after we've had all this rifting and extension, we have the thermal subsidence phase. So it's the basin, everything cools down, everything thermally subsides slowly, and you get a whole lot of sediments generally put in on top of that. Those sediments tend to obscure what's going on down below. So if we can remove those sediments, remove their gravity effect, then we can look at the gravity signature of the crust at the time of the rifting and the extension. And that's going to give us some important information about what was happening at that time of rifting. So the idea then is to backstrip the post-rift sediments. So we take them out to see what's left behind, and it would in a simple case look something like this, of course. We do that for various values of this parameter here, TE, which is the effective elastic thickness, so that's a measure of the strength of the lithosphere. So we can assume, okay, when those sediments deposited, the lithosphere was really strong or it was weak, and we do that for several different things, and we get our rift-related crustal structure. That's what's shown here. The sediments that backstrip out have their own gravity signal, and you can see here for a high TE, so quite a strong lithosphere, have quite a high positive gravity anomaly. And that's a positive gravity anomaly associated with low density sediments. And it's important to make the point there that you can have a positive gravity anomaly with those sediments because they're sitting up on top of a strong lithosphere. So they're sticking up out of the plate. They're not compensated for anything down below. In contrast, when you have a much lower TE, you have a much smaller amplitude anomaly here. So we've broken this down into the gravity effect related to the rifting, which we can then use to infer the crustal structure at the time of rifting, the gravity effect of those sediments. What we would then do is combine the two, put them up here, and we can compare this then to our observations. So this would be the model gravity that would come out, and we would compare this to our observations. And in this case, sediments loaded onto a lithosphere with a TE of about 20 is probably what's giving us the best sort of result. So it's about taking out the sediments to try and see what was there before those sediments were there. And I'm going to demonstrate an example of that from the Browse Basin. This is a map here of the Browse Basin. You can see the Western Australia here, the Kimberley block. It's got these shallow shelves out here, the Yampi and the Levesque shelves, which are basically an extension of the Kimberley block out into the basin. There's the Caswell sub-basin here, which is the main epicenter in the basin, which hosts all of these large gas fields, which are well on their way towards development. And further out is the Scott Plateau, a submerged plateau. Probably the best way to see this more clearly is to look at a seismic section through here. And here's that seismic section starting on the Leveque shelf, the quite shallow sediments. This would be the Kimberley block coming out underneath. The Caswell sub-basin here, where you've got something like up to 15 kilometres of sediment in underneath the basin, and then out onto this submerged Scott Plateau here. In terms of stratigraphy, let's just simplify that for today's purposes and lump everything before the actual rifting that led to breakup into a pre-rift sort of sedimentary sequence. There's a lot of stuff caught up in there that's going to be pretty important that hasn't been considered to this point in time. There's a little bit of syn-rift sediment here, which is the sediment related to that crustal extension. And then there's this big thick sequence of post-rift sediment. So these are all the sediments that have been put in there after the rifting during this thermal subsidence phase. And these are the things, because of their load, they've deformed the crust underneath. They've kind of obscured the crustal structure related to what happened at the time of rifting. So these are the things we want to try and get out. So our idea then is to backstrip those sediments out to see what's left behind. And we can backstrip that out. We don't have to do it in a single layer. Here's those three isopacks for the different sedimentary layers that make up those post-rift sediments. That allows us to take an account of increasing density with time. So as these sediments get buried and put deeper, they lose their porosity and become more dense. It also allows us to change the strength of the lithosphere with time. So we can assume that, just after rifting, when everything was quite warm, the lithosphere was probably much weaker than it is today. So we could say, for example, it's weak then and strong when these sediments were deposited. And there's a whole range of obviously different combinations we could try, and I'm only going to show you one example today just to save time. And what's shown here is the results after these sediments are backstripped out. So on the left-hand side, this is what we term the backstrip basement, or the total tectonic subsidence. So this is essentially what the seafloor would have looked like before all those post-rift sediments were deposited on top. And if we can infer that kind of thing, then we can use some kind of assumptions on isostasy and things as well to say, well, what's the crustal structure in this area? So this would be the crustal structure we get from the backstripping modelling, this process-oriented modelling, the crustal structure related to the rifting in the Browse Basin. So how do we know how good that is? Well, there's two things we can do. We can obviously look at the gravity data. So this again is the observed gravity over here, the observed free air gravity. You can see this edge here, the Caswell sub-basin, the shelf areas here, and the calculated gravity is here. And so this is the sum anomaly, this is the gravity effect, combined gravity effect of the rifting and the sediments. And this is what we obviously want to have look a bit like this. And you might think at first glance, they're not very similar, but you can see the low here that's associated with the Caswell sub-basin. And we can look at the difference here, and we can again argue about how good the fit is here. But generally it's not too bad a fit. The other thing we can do, of course, is compare our results to independent observations. And it happens that we have one refraction profile which crosses the Browse Basin up in here. And we can look at that profile, compare the gravity and the crustal structure that we get. And that's what's shown in the next slide here. So up the top, you can see the gravity section here. So there's a dashed line here, which is the observed free air gravity anomaly. The solid line is the calculated gravity we get from this crustal configuration here, the coloured model here. So the yellow represents the sediments that have been backstripped out. The MOHO inferred from the modelling is this boundary here. And we can compare that to the MOHO that comes from the seismic refraction model. And your immediate impression is, well, there's plenty of places that don't fit there. But that's okay, because this is a model that doesn't fit. And that's the kind of model that I'd argue is going to tell you more about one than I just showed you that fits everything, because you're not going to know how I got to that point. So I can now look at this sort of model and say, okay, well, what kind of processes have I not considered in the evolution of the margin that should be maybe included in this model? And they would be things like magmatic underplating. Is there evidence of magmatic underplating in here that's thickened the crust, changed the way that the loading has occurred? Pre-rift extension. I told you at the start I lumped all of that pre-rift stuff into a single layer, which I ignored. But there's been a whole lot of earlier extension, which has obviously also shaped this margin as well, that needs to be somehow considered too. There's also this effect of the load of Timor on the Australian plate. As the Australian plate is subducting to the north, Timor is loading the plate, which is bending the plate, and we're getting some kind of flexure of the margin as well. And largely the misfit that's shown in here, and I'm not going to show it now, but you can ask me about it, we can account for a lot of that misfit by taking account of this load of Timor onto the elastic plate. But overall, we can see a reasonable fit to the edge effect anomaly in here. So we've got some kind of indication of crustal structure. But like I said, it's early days, and there's a little bit more to do on this work here. So just to summarise this process-oriented modelling, well, it's a method that, like I said, Tony Watts has worked on extensively applying this method in other parts of the world and come up with all sorts of interesting results. It's never really been applied on the Australian margin, and I think we have some potential to gain information on the Australian margin by following this sort of approach. And we're trying to keep some contact with Tony Watts, and he is going to have a fourth-year student work on the Northwest Shelf sometime over the coming year. So the crustal structure we infer for the Browse Basin, it's broadly comparable to the MOHO from the seismic refraction data. There's obviously misfits that tell us something about other processes. It also, of course, maybe tells us something about the refraction model. Is the refraction model ideal? The MOHO misfits that I've talked about these processes here. So is there magmatic underplating? Does that have to be accounted for? Earlier pre-rift extension and the flexural effects of Timor loading. Okay, so I've pretty much come to the end now, and I think what I've tried to show you is some examples of sort of in this part of the basin analysis workflow that Heike Struckmeyer sort of put together here. And I think these sort of examples here hopefully demonstrate to you how we link potential field data together with all the other information through these sort of approaches towards the petroleum system modelling. And so the potential field data has a critical role to play in all of that. Okay, so just in summary, hopefully I've demonstrated to you that gravity and magnetic data have plenty of useful applications. They're a useful aid to interpreting the seismic data. They can give us extra information, test our interpretations, are they any better? They can help us characterise the basement and what the crust looks like. And they can also help us quantify structural trends. And that's something I haven't touched on today because it's just not enough time. But again, you can ask me about that if you wish. I'd like to leave you with the argument that the offshore parts of Australia really lack constraints on crustal structure. And if we want to be really good at doing more about the crustal structure and how that relates to all these basin processes, we could really be looking to go out there and get more of this kind of data. Then the last question is, can we be smarter with our modelling? And I think we can. This modelling while interpreting approach that I showed you from Peter Petkovic, I think was quite successful in the Capel and Faust Basin and gives us some extra handle on the uncertainty associated with some of those key parameters related to petroleum systems. And then this process-oriented gravity modelling is applied quite successfully around the world, but perhaps some opportunity to apply it more around the Australian margin. So, we can skip that now. As I switch to thinking about how we're going to use this nice new Browse Basin airborne magnetic data that, like I said, has just been released today, I'm happy to take your questions. I'm happy to receive your feedback and comments, and thanks for your attention today.